And if I just sort of rewind the tape a little bit here, now that we know what we're looking for, let's actually start looking for it. I need that minus sign up there again. The problem with making a mistake on tape is that the mistake is still there when you rewind the tape. Anyway, hopefully that's fixed. So the three different moves that make up what we call the elementary row operations, one of them is that we can interchange two rows. I call it swapping. Swap two rows. That shouldn't make a difference to our solution because, after all, each row just corresponds to an equation. And if we're trying to satisfy all the equations simultaneously, it doesn't matter which order we write the rows in. We write the equations in. So one of the elementary row operations is that we just take two of the rows and we interchange them. And when we do that, the left-hand sides of the equation swap, and so do the right-hand sides. And so the entire row of the augmented matrix swaps. That's one elementary row operation. What's another? The other two, by the way, are operations that we did at the level of the equations yesterday when we used the elimination method.
Multiplying one row by a certain number.
Sure. We considered this to, and we will consider this still to be a setup move, kind of. Multiply a row, an entire row, by a constant. I'll just put a number here. Yeah.
How do you know what row to multiply and what?
That's where the strategy, that's where our strategic thinking comes in. So when we look at this example, I'm going to try to be hyper-strategic about it, and we'll develop that sense. But that's the efficiency part of the puzzle. So yeah, we'll get to that. So multiplying an entire row by a number was a step we used yesterday in order to set up so that the coefficients of a variable are either equal or equal and opposite, so that we could then eliminate that variable. But then at that elimination step, what are you doing to those two rows? Adding them, or possibly subtracting them. But subtracting is the same as multiplying by -1 and then adding. So to be completely general, let's just make that our third move. Add two rows together. And then with that sum, we can replace either of our original rows. Add two rows and replace one by the sum. Doesn't matter which. And these are our three moves. So row operations, row reduction, if you like, is nothing more than kind of like playing a game. And here are the three rules of the game. Right? These are the three things that we're allowed to do. We know what the goal is. We know how to win. So it's just a matter of finding the right sequence of moves such that we hopefully win as quickly as possible. So let's take a look at our system that we have up here and get the process started. So what would you like to do for your first move here if we know that what we want is ultimately to get a matrix in upper triangular form? So again, let's get our target lined up here. That we want a matrix that's in upper triangular form, so we would like to maybe have ones on the diagonal, other stuff up here if we need it, and then some numbers over here that are going to help us to actually find the values of these variables. But if what I want is to get a matrix that looks like this, and by the way, I think Ley uses this shortcut, and I'll occasionally use it too, that if we have zeros in a matrix, sometimes we'll just leave them as blank spaces to make it a little easier on the eyes. For now, I'll keep them in, but in case I ever leave an entry in a matrix blank, it means that there's a zero there. So how are we going to pick a first operation here? What would you like to do to get the process started? We can either swap, or we can multiply a row by a number.
Would you swap the 0 and the 2 row? -2.
Yeah, how come why is that a good choice to begin the process with a row swap? What are you trying to accomplish there?
We want to get the highest number on the top, or the highest number in the column on the top.
Well, as long as, let me put it this way, starting from the end, I'm going to focus on this one, this pivot that we want in the upper right, the first column's pivot. At the very least, in order to get that, we want to start with a row that has a non-zero entry in the top left. So in order to have that 1 there, I need to make it so that the 0 that we're starting with over here is not there anymore. But I can't move that 0. Well, I could move it in a variety of different ways. I could either just move that row down, which is kind of nice, because if we have a 0 in this process, we kind of like to hang on to that 0. Because ultimately, row reduction is about creating zeros where there were no zeros before, namely those zeros below the diagonal. So I think it's a good choice to swap this row because it already has that 0 that we want. So what we could do is either take this row and swap it down to the end, which would create for me this 0 in our answer. Or we could swap it with the second row, and that would create for me this 0 in my answer. So either way, we're winning. Just for the sake of fun, let's swap the first row with the second. Again, it doesn't really matter, but I also, in addition to liking zeros below the diagonal, I also kind of like 1s on the diagonal, if we can get away with it. And we'll develop an appreciation, I think, a sense for why in a second. So let's begin our row operation process by swapping the first row and the second row. And when I do that, I like to keep track of my operations just in the margin over here. So swap row 1 with row 2. And what I end up with is 1, 1, negative 2, 1, 0, 3, negative 2, 6, negative 2, 5, 1, 1. And now let's get our matrix brackets in there. And our augmented matrix line. There we go. So again, the reason that we've made significant progress is that we have now gained this 0 below the diagonal, which we want. Right? So the process of row reduction is by kind of trying to pick on an entry, like our 1 in the upper left that we have now. And now we're trying to do whatever is necessary to make that entry into a pivot. So it's about discovering pivots, maybe is another way to think about what row reduction does. And again, a pivot is a non-zero entry. So first of all, we had to make that non-zero. That's what the row swap accomplished. But then it also has zeros to its left and zeros underneath. The zeros to its left are not a problem because there's nothing to the left at all in this matrix of the entry that's circled. So to continue the strategy, let's work on the zeros that we want beneath it. We have 1 0 beneath it now. Let's get another. So what entry do I need to focus on now getting rid of to make that circled 1 into a pivot? Let's get rid of that negative 2.
You multiply the first row by negative 2.
Let's multiply it by positive 2.
And then add it to the third row.
Yes. Why'd you choose positive 2 again?
Well, that way you'll get a 0 for the negative 2.
Exactly. So just like when we were doing elimination yesterday, the purpose is to kill something. It's not to put too violent of a metaphor on it, but the purpose is to get rid of that negative 2 that's in the box by adding it to a positive 2. Well, we need to make that positive 2 somehow. This is why I like having 1s on the diagonal, because then all I have to do is multiply that 1 on the diagonal by the positive 2 that I want, and then we're set up in exactly such a way that, and again, keeping track of this operation, we're taking twice row 1, and we're adding it to row 3, and the result, we're going to stash in row 3. So we're going to replace row 3 by the sum of itself and twice the first row. And that is going to accomplish getting rid of the negative 2 that's in the box there and making it a 0. And row 1, I'm going to keep the way that it was, because I kind of liked that 1 that was in the first position there. 0, 3, negative 2, 6. So row 2 doesn't change. But row 3, now, negative 2 plus 2, 0. 5 plus 2, 7. And 1 plus negative 4, negative 3. And 1 plus 2, 3.
Should be 14, I think.
Yeah, what did I screw up here?
You just forgot to put the 12
Oh, yeah, you're absolutely right. Yet another problem with trying to rewind the tape if I didn't rewind it far enough. I need this 12 in there. Thank you. And so you're right, 14 is exactly what we want. Okay. So this is a major victory for us now in our strategy. Because we've accomplished, in these first two steps of row reduction, making that entry into a pivot. This is now an honest-to-goodness pivot. Because it's a non-zero entry, everything below it is 0, and everything to the left of it is 0. And so that column now is done. I'm just going to kind of put a done proclamation down here at the bottom. So when I'm thinking about being systematic about row reduction, what I'm usually thinking about is, let's focus on that first column for a second and try and see if we can elevate some non-zero entry, which we had to do here with the row swap. Elevate some non-zero entry as high as we can, and then do whatever is necessary to make it a pivot, to clear out all the non-zero entries underneath it so that they become 0. So going back to our original, it's kind of like, here we are, we want to focus on making all that stuff underneath that entry go away. And now we've done that through the choices of row operations we've made. So now we've cleared out the first column. How about the second? Where am I going to look in that second column for a pivot? A new pivot.
Move the 7 to be a 0.
Wait, say that again?
Looking at the 7 and call out.
Right, we want to wipe out that 7. How come we don't want to wipe out the 3 out of curiosity?
You need that to be 1.
We would like for this to be non-zero. Why? So I guess what I mean by my question is, how come we don't want to try to make that 1 into a pivot? We want the diagonal, because there can be at most 1 pivot per column by definition. So as long as we still have that first pivot taking up the upper left-hand corner, we can't make the second one into a pivot because it's not going to have zeros to its left, because it has a pivot to its left, and pivots are non-zero. So in other words, let's focus on that diagonal entry. Let's focus on that 3. Let's try to make it into a pivot. What would you like to do first? Again, try to clear out that 7.
You go for the first row by -7.
Okay. The first row or the second row?
But when you do the first row and then you'd add it to the third row, and the 7 would go away, and the 3 would turn into a -1.
I agree with that. But here's my word of caution, is that if we're trying to be efficient about this, if I were to do something like multiply the first row by 7 and add it to the third row, row 3, then I'll achieve my goal of getting rid of that 7. But I'm also going to end up undoing some of my progress from before. Right? That 1 is now going to turn that 0 that we won down at the bottom into a 7. And that's kind of, it looks like a step forward because we wipe out the 7 right there, but it's almost also a step backwards because we're making something that used to be 0 into something not 0 anymore. So again, thinking about strategy, that as soon as I have finished clearing out a column and creating a pivot in the column, I'm also going to say to myself, I'm done with that row too. So this row and this column, now that I've found my pivot, and there can only be 1 in each row and column, now I'm just going to forget about that side of the matrix altogether. And now to clear out that 7, instead of using row 1, let's use row 2. Which, from a number theory perspective, looks more challenging. But it will help us to keep the progress that we've made in this row reduction so far. So how do I clear out the 7 using the second row? Because 3 and 7 are relatively prime now, which is the irritating part.
Multiply the second row by 1.
Okay. So we'll use move number 2 here. Let's multiply the second row by 1/3. And that will have the effect of creating for us a 1 on the diagonal. And we like 1s on the diagonal. They make life much nicer. So where we had a 3, now we'll have a 1. Where we have -2, will now be -2/3. So there's the price we pay for this, is now we've got some fractions populating our matrix. Not the biggest deal in the world, but whatever. Luckily, the 6 over here is commensurate with 3, so that becomes a 2. Okay. Now it seems to be much more tractable to get rid of that 7 using what operation? How can I wipe out that 7? Using row 2. Negative 7 times row 2. Yeah. So that the circled 1 here is going to turn into a negative 7, that when I add it with a 7 in the row below it, will make that entry into the 0 that we're looking for. So, if I multiply this row by negative 7, I'm going to get negative 7 here. I'm going to get 14 thirds over here. I'm going to get negative 14 over there. Now when I add that to the third row, let me clear out some space here. Add that to the third row, and the third row is going to become 0, 0, and then negative 3 added to 14 thirds is 5 thirds. I think I have that right. And then 14 added to negative 14 becomes 0. All right. And the good news is, in that process, not only, so let's rewrite the second row in here again, 0, 1, negative 2 thirds, 2, 1, 1, negative 2, 1. Put in our dividing line again. Not only did we succeed in creating a pivot in that middle entry at the 1, we've also succeeded in creating a third pivot, namely the lower right-hand entry, 5 thirds. So here's our 3 pivots. And the only thing I want to do now is let's make that last pivot into a 1 also, just so we have a really nice looking matrix here at the end. How do I turn that 5 thirds into a 1? Just multiply the third row by 3/5. Yeah. Okay. And luckily 0 times 3/5 is still 0. So here's our matrix. It has 3 pivots in them. In other words, it has a maximal number of pivots for this matrix. And all of its pivots are 1. One more piece of terminology for you today, before we turn you loose into your pairs to do an example of this, and to, again, think about strategy. That a matrix in this form is said to be in row echelon form. In other words, all the pivots are identified, and all of them are 1. So here's our matrix in row echelon form. And all we had to do was a series of elementary row operations to get there. So let's just finish this example by turning this row echelon form, which, by the way, the purpose of any one of these elementary row operations is to create a new system of linear equations that has the same solution as the original. Because swapping rows doesn't change your solutions. Multiplying an entire row by a number doesn't change the solutions. Adding 2 rows together doesn't change the solutions. Right? So the solutions are what stay the same in this whole process. Even if the equations, in other words the matrix that we use to represent this system, look different. But that means that we can solve the original by solving the row echelon system. So we'll just take the row echelon system and turn it back into equation form. And because it's in row echelon form, what does the third equation tell us? Z equals 0. Yep. So the first one of our solution values has now been found. So x, y, z equals something, comma, 0. And now that we know that z is 0, it's time to back substitute. So z equals 0 substituted into that second equation. The second equation reads, in equation form, y minus 2/3 z, but z is 0, is equal to 2. So what is y? 2. Here's another reason why it's nice to have 1s on the diagonals, because all you'll ever have to do when you back substitute is add and subtract. There will never be any multiplying or dividing necessary in this step of the process. So now that we know that y is equal to 2, we can take both of those values and substitute them into our first equation, which then reads x plus y minus 2z equals 1. But we know that z is 0, and we know that y is 2. So x plus 2 is equal to 1. Therefore, x is 1 minus 2. And then we're done. So this back substitution step at the end seems positively straightforward in comparison to all the row operations that preceded. Which means that really the goal is to get to row echelon form, because once you're there, the rest is downhill. Downhill in a good way, like sledding downhill, not falling downhill.
You guys do this, that would be your final.
Right, so then if the question is to solve this linear system, your final answer had better be, tell me what x is, tell me what y is, tell me what z is. And in this example, x is -1, y is 2, and z is 0. So how many solutions did this linear system have? It had one value for x, one value for y, one value for z. That's one solution. Right? There's only one possible answer to this question. It's this value for x, that value for y, that value for z. So again, even though there are 3 different variables, they form a single solution. In other words, a unique solution. So this is a consistent system, and its solution is unique. Namely, this triplet of values is the unique solution.